Hi everybody, welcome back to Soft Magnetics.
Hard topics.
So today we're going to be talking about characterization of parts at home, right?
You didn't introduce yourself.
I'm Bridget.
I'm Mike.
And we're going to talk about characterizing parts at home. Can you do it?
You can.
Tell us how.
Okay, so it's kind of I guess a little bit of a follow-up to that video from 5 years ago in my garage when we weren't allowed to go to work.
Yeah. Check it out.
Yeah. So in that video, we looked at using a couple $100 LCR meter.
Yeah.
Which, relative to test equipment, is pretty cheap, but I realize that's not nothing still.
Yes, yeah.
So we want to take a look at the ever popular NanoVNA. So we wanted to take a look at what the NanoVNA, this can measure much higher frequencies than a little pocket LCR meter.
Mm-hmm.
So this particular model that we got here is the 50 kilohertz to 3 gigahertz model. It was, at least as of the time of this video,
yes,
around about $100.
Yeah, something like that.
And that was, I think, kind of the mid-tier one. I think there was one that was like lower, 50 and one that was like 200. So we wanted to take a look at what can you actually do with this to measure impedance up at megahertz, hundreds of megahertz kind of frequency ranges that you'd normally see a Fair-Rite core spec'd in. And we also wanted to take a look at how that compares with the normal types of test equipment we would use at a manufacturer like this. So we compared it to our E4991A Impedance Analyzer that's made by Agilent. That's now Keysight and was formerly Hewlett-Packard.
Yes.
So a couple changes there. That piece of test equipment is, orders of magnitude more expensive than something like this.
Right.
You're talking not hundreds, but tens of thousands of dollars for something like that. I think the newer ones are even more than that.
Mm-hmm.
But we want to take a look at what this can do against a piece of equipment like that. For the test setup for this, we used a shunt through method, wherein we basically connected port 1 and port 2 on this NanoVNA, and then had a little T-junction there that we use for our device under test fixture. And then we were simply measuring, after all the calibration and all that stuff, we were measuring basically log magnitude on port 2, so S21 on this, and using that in our phase angle to get our data, similar to what we would do on the impedance analyzer. So I guess
stay tuned. Mike's gonna take over, and we'll be right back.
Take a look at that. Here's everything that we're going to use to perform our impedance analysis. Starting off, we have our NanoVNA. So this is a version 2 NanoVNA. This particular model, I believe, is the 50 kilohertz to 3 gigahertz model. I could be wrong on that. We'll post a link to it in the description. We have a Fair-Rite core. We need something to analyze with our impedance analyzer. This is 44 material oval snappet core. We have a T-junction here. This is going to be part of our test fixture that we're going to use. Binding post adapter. This is going to be another portion of our test fixture. You have included with the NanoVNA, open, short, and load here, 2 cables. And a test lead, since we're going to need something to test through. So let's start with the setup. Now, I updated this NanoVNA to run the latest software revision. I don't know that it actually makes any kind of performance difference to the readings, but it does allow you to save a CSV directly onto the unit rather than having to have it plugged into a PC the whole time. So for convenience sake, that was pretty nice. So let's go through our test calibration setup. So right now we have this set for a 100 kilohertz to 1 gigahertz sweep using 200 data points. And for the test setup, we're going to go ahead and connect our leads in here. All right, now we have these connected. We're going to take our T and T it into port 1 and port 1 only right now. And I should say for our measurement setup, what we want to look at on the screen here, actually let me disconnect this so you can see a little bit better what we're actually looking at on here. So we want to look at under display, trace, we want trace 0 and trace 1 active. And for both of them, we want to be on channel S21 on here through. And then for format, the two that we want to use are going to be on trace 1, log magnitude. For trace 2 or 1, we want to be looking at phase angle. Okay. On to the calibration. So we want to be looking at using one of our adapters here on this third port on the T. And we're going to do most of our calibration on port 1 using this third port on our T. So we're going to go down to calibrate. And then it's going to prompt us to put our open on first. So we're going to put our open on our T. Press open. Rinse and repeat for your short. Put that onto our third port again. Press short. And our final standard is going to be our load, again on that same port. Now, there's a through option right down here. That we're going to do with port number 2 connected on the VNA. Like so. Then we have to take our adapter, bonding post adapter, screw that on. So this is going to be our DUT or device under test port right here. So with this on, no DUT attached, we're going to do the through measurement. Now that we're done, prompts us to save. So we'll pick save slot 3 on here. You can save up to 6 calibrations on the NanoVNA. And with that, we are ready to measure. So what you should see at this point is your, well, I set up a couple markers ahead of time, but you should see mostly 0 dB across your entire measurement span here. Now, it's not perfect. It's not a perfect calibration, so we get some kind of noise and artifacts up here, up at the higher frequencies. But down where our measurement points are, which in this case is 100 kilohertz, 100 megahertz, and roughly 250 megahertz, about as close as this can get to 250. We're at pretty much 0 dB. So next step, we are going to snap our core closed, like that. Put our test lead through, attach it to our binding post fixture here. All right, so now we no longer have 0 dB. We actually have some attenuation here. And our phase angle's moving. So we could take this reading here, and we may want to actually auto scale our display here. All right. Well, you can see we actually have some readings on the screen here. We can go ahead and save this. So if we go under storage, save CSV. Now that wrote it to the memory internal to the NanoVNA. We can pull that off onto our PC and show you how to analyze that in terms of ohms rather than dB, which is what we're seeing on the NanoVNA. Now for the other end of the spectrum, we have a real deal 1 megahertz to 3 gigahertz E4991A Impedance Analyzer. Now this is a dedicated piece of test equipment for measuring impedance sweeps over frequency. Also serves a lot of other functions like measuring inductance, resistance, capacitance, things along those lines. Now we're going to take a look at how this part measures on this analyzer. So starting off, we're going to calibrate it, much as we did with the NanoVNA. To do this, we have our open standard, short standard, load, and this one's a little bit different. This is a low loss capacitance standard. Now to do our calibration, we are going to go to the cal menu on this machine, and we are going to select the calibration. Very similar to the NanoVNA so far, we're going to put our open standard on. So that screws into our test fixture like this, and kind of on the theme with the level of precision that this offers, we actually are going to tighten this down with a torque wrench to a very specific torque. So click open, performs our open calibration. Okay. Short is up next. Torque down. final standard getting measured. Okay, we're going to hit done. That'll apply our calibration. Now, here is where this is going to start differing a little bit from the NanoVNA. Open short load measurement, that's pretty similar. The capacitance standard, that was a little bit different. But one of the areas where the impedance analyzer starts differing greatly is the fact that we can select a fixture type here. Now, to actually do our measurement, we're going to use this test fixture. So this is a 16092A spring clip fixture. So you can see from the Hewlett-Packard logo, it's an oldie, but it's a goodie. Now, this fixture is going to go onto our APC7 connector right here. And I'll put that on right now. Screw that down, same as the standards, torque it. Now, this fixture isn't actually one of the selection options inside here, but this fixture has a defined electrical length on it, you might be able to see, of 3.4 millimeters. Now we can actually select a user fixture on here and define a custom electrical length. So we select user, 3.4 millimeters. Now our fixture length is set, and we can go ahead and compensate. So we did the calibration on the APC7 connector, but we can go a step further on this machine and actually compensate for the fixture. This is something that we aren't able to do on the NanoVNA as standard in the software. We can go through and do that after the fact, take a short trace, an open trace, and use that to correct our values that we get after the fact. But on here, you're able to do it directly on the machine. So the fixture unloaded, no DUT present. I'm going to hit open. And then we are going to place our gold shorting bar inside the fixture. I don't know that you can see this too well. We're going to place that into our fixture. You can see this drop down to almost 0 ohms. So we're going to hit short. Done. Now on the bottom of our screen it says Cal Fix, compensation on. Now we're ready to measure. Back over to our test fixture. Take our shorting bar out. And now we can place our part in. Okay. So that is in our spring clip fixture now. Scale this. Now, a kind of neat thing that these meters do, when you change the markers around on here, you can actually interpolate between the data points that it's actually measuring. So this is doing a similar thing of measuring about 200 data points between 1 megahertz and, in this case, 3 gigahertz. But you can set a marker, so as I'm scrolling through, it's hitting the individual data points that the machine's actually measuring. But if I want to hit something like, say, exactly 50 megahertz, we can do that, and it's going to give me the 50 megahertz reading because it's kind of filling in the blanks between the actual data measurement points. So we're going to pull some traces onto a nearby PC for this part and a few others, and then we'll take a look at how those compare with each other. Here are our measurement results. So we have a plot here of that 44 material oval snippet that we measured. The orange line at the bottom is what we got off of the E4991A Impedance Analyzer. And the blue plot is what we saw on the NanoVNA. Well, not directly what we saw. The raw data that we got in here is in column B, so this is the log mag S21 readings that we saw on the screen. That was saved to a CSV, and then we imported it into Excel. So we had to convert that over to linear magnitude in column D here. And then since we're using a shunt through method, we had to multiply the linear magnitude over the reciprocal of the linear magnitude multiplied by 25 ohms to get our impedance of the part. Now the two plots, there is definitely an offset between the two, but they do follow pretty similar trends up until you get beyond 100 megahertz. I think a good portion of this is probably down to the lack of fixture compensation on the NanoVNA. That could probably be corrected, and maybe we'll look at that in a future video of using the delay function on the NanoVNA to somewhat correct this offset. I also measured off camera a 31 and 61 material core, same geometry, just different materials. Now, interestingly, the 31 actually at lower frequencies traces the 4991 impedance analyzer a lot more closely than the 44 material does. I assume a portion of this is due to the higher loading, since 31 material has about 3 times the permeability of 44. And we see up through 10 megahertz, they trace a lot better one another. The 61 is kind of the opposite. So at low frequency, they are surprisingly close to one another, but beyond 10 megahertz, the difference between the two starts deviating a lot more than what we saw on the 4991A impedance analyzer. So yeah, there is a difference between the two, but can you use the NanoVNA to make some basic measurements? I would say you could.
All right, so we're back. We're tested.
We're tested.
We're compared. And Mike, you went over all your findings.
Yeah, so I guess we could summarize those. You can, in fact, make impedance measurements off of a NanoVNA. It is possible. Takeaways are, you know, it's maybe not the most accurate thing, and a lot of that's going to be down to how it's fixtured and the calibration. And I think actually probably a neat follow-up video we could do is we could take a look at how to make that measurement better than we did. But this video would be very long if we went into all that here.
And now we have it.
And now we have it. So yeah, you can make measurements. Can you do, you know, for us as a manufacturer, can we QC parts using a piece of equipment like this? No, it's not really good enough for that. When we need to measure stuff, you know, within a % or a couple % repeatability to be able to say whether a lot of parts is good or characterizing new materials and making published data, it's not really good enough for that. But if you had a couple cores and wanted to see what
Yeah.
sort of impedance values that they measure out at, yeah, you could probably do that with this.
Very cool.
We may even take a look and see if we could do some material characterization. So on all of our data sheets, we have those fun, complex permeability curves. I mean, in theory, you have the Z, you have the phase angle. You can get perm from it. So we'll take a look at doing that in another video and see if we can actually generate some catalog curves.
Wow.
I mean, we won't publish them, but I'm,
We
curious,
try.
I'm curious to see how close it gets.
Yeah, definitely.
So yeah, we can go over all that in another video.
Very cool.
Yeah.
I think, we appreciate everybody, and we're so close to 2,000 subscribers that if everyone can subscribe and get us to 2,000, we will give away one of these to one of our followers and subscribers. So be sure to subscribe, like, comment anything that you want us to go over next, and we'll be coming back with more videos with this.
Sure will.
Cool.
Gonna get some mileage out of this puppy.
Yeah, I know. Well, thanks for joining, and see you soon. Bye.